This lesson here is kind of the main focal point of our whole unit. We've been building and building and building to get to this particular point. So we've talked about oxidizing agents, reducing agents, the whole concept of redox, right? We've beaten that to death. I'm hoping by now you guys feel fairly comfortable with me talking about an oxidizing agent and you know what I'm referring to, right? We've talked a little bit about how to balance reactions, and we've learned one practical use of a redox. That would be a titration. Okay, this is probably the most common use of redox. It's called a cell, but a cell is really the fancy word for a battery. Shoot, where did I leave my little stick thing now? Here it is. Okay, so I did this silly demonstration earlier. I don't think I'll actually do it again, but imagine that this is an electron, and the electrons have to go from my right hand to my left hand. Okay, who's the oxidizing agent? Who's the reducing agent? Okay, so let's walk it through. This guy right here is going to lose electrons. If you lose electrons, this guy is being oxidized. Therefore, this hand is the reducing agent. So it goes from the reducing agent to the oxidizing agent, right? Now, normally, in order for things to gain and lose electrons, literally the electrons have to come in contact with each other. But this is where a cell is brilliant. If I were to take this electron right here, and rather than go directly from the oxidizing to the reducing to the oxidizing agent, if I were to pass it around the room and then come to here, I've made a circuit, right? And this is brilliant. This really has, I really do believe this. This has fundamentally changed our lives because we now have portable electricity, right? And now think of all the devices. I mean, at the very least, you're talking your calculator, your cell phone, right? I mean, even little things like pacemakers able to occur because of the fact that we can actually run a current without it having to be directly tied into an electrical grid. Does that make sense? So today's long lesson is basically going to discuss a lot about batteries, different ways in which we can use this, and it's just a really clever technological way of designing it. Is rather than going directly from right hand to left hand, we just go around the loop. Okay? So I want to begin with a couple of definitions that I want to make sure everybody's aware of. This has a huge overlap with some physics stuff. So you guys that did physics last year, some of these terms should be familiar. For those of you guys who haven't done it yet, we're doing that next year. Okay, so the first definition you guys can read there. Electricity is really the movement and flow of electrical charge. But we could probably be more specific than that. I mean, what are the two types of charges? Electrons and protons. Which one actually flows, though? Yeah, because where are the protons tied? In the nucleus. A bit of a history lesson. Back in the days of more or less Ben Franklin, you probably heard the story of him and the kite, where the electricity hit the kite and he discovered electricity. Anyone ever heard that kind of story there before? Okay. By the way, that's actually not true. It wasn't him, it was his son. He made his son do it, so it was really nice of him to not take the bullet of holding onto a kite in an electrical storm. Anyways, they basically had to decide whether or not they wanted to. They knew about different charges. They knew there were positive and negative charges. But at this point here, they had no idea of the internal structure of matter. They did not know about nucleuses and electrons. They knew positive and negative. And so they just had to randomly pick one. And so they actually picked positives to be the charge that moved. And then years later, we discovered it actually wasn't the positives that moved. So do you guys in physics remember what we called the opposite of regular current? Nice. Yeah, it's called conventional current. If you ever come across the term conventional current, it's the idea of, what if positives moved? We now know that positives don't move, but if you can put yourself in the mind of somebody 300 years ago, they had to pick either the positives or the negatives to move. They didn't know which ones were which yet, so they just picked positives to move. Whoops, wrong choice. That makes sense? So anyways, that's why electricity is known as the movement and flow of charge, but we can be more specific. It's electrons, right? We know that much. Now we can measure charge in terms of a unit called a coulomb. Okay? It's very similar to a mole. You guys know how a mole is basically it's a whole lot of atoms, and rather than counting them one at a time, we count them 6.02 times 10 to the 23 at a time. That's a mole of atoms. In the same way that rather than buying donuts individually, we often buy them by the dozen, right? Well, a coulomb is a measure of charge. And this I pulled directly out of the physics data booklet. If you're familiar with it, because you took my course last year, that's awesome. If not, don't stress too much. But the basic idea is that one electron, if you could actually isolate just a single one, this thing's not doing good today. Come on. If you could isolate a single electron, it would have a tiny amount of a coulomb. So one electron equals this partial amount of a coulomb. I find it actually better to look at it the other way. If I were to type out 1.6 times 10 to the power of minus 19, that is a fraction of a coulomb for one electron. If I wanted to then figure out how many electrons are in a coulomb to make up one full coulomb, if I take the reciprocal, this number right here, if you want to write this in, there are 6.25 times 10 to the 18 electrons in a coulomb. So similar to how a mole is 6.02 times 10 to the 23 atoms in a mole, there are this many electrons in one coulomb. Does that make sense? So if I ever see 1Q for like one, well, I should probably not use Q. We'd probably use C. If I used 1C, it means you have that many electrons. If I gave you 2 coulombs, it means you have this many electrons times by 2. If you had 0.1 C, it means that you have this many divided by 10, because you only have like a tenth of it. Does that make sense to you guys? And so that's how we measure our electricity. We measure it based on how much charge there is. And these moving charges, these moving electrons, depending on, I don't know, how much energy they have and how fast they move, that's how we measure things. Okay. And these are actually 2 other words that I'm sure you guys have heard at some point in your life. Darian? Why did they choose like that number? It had to do with Millikan's oil drop experiment. Do you remember that experiment there where he had the oil drop and then he hovered it between the 2 electric plates and then gravity would pull it down and that would pull it back up again? That's what he calculated was the fundamental charge of an electron, right? So what he did is he managed to determine that it was always in multiples of 1.6 times 10 to the minus 19, and so therefore he determined that must be the charge of an electron, right? And that actually is, like, if you remember your physics data sheet, not only was that like how many coulombs to electrons there are, but that was actually like the charge of any particle. Do you remember this at all? Yeah, it's been a while. Good question though. It's going to take a lot longer to explain to everybody else. So, sorry guys. That was a good question. I will tell you next year if you're in grade 11. I promise. Okay. You guys ever heard these words before? Current and voltage. They're the 2 most common ways that we measure electricity, but they are different. They are very fundamentally different, and you need to make sure you don't use them interchangeably going forward because there's a huge difference. So let me give you a couple of analogies that I like. The first one, I'm going to hop ahead to another slide I've got here. It's the water tower slide. And I'll use this as my analogy and I'll come back again. Imagine that you have a big tower of water above the ground. Okay. And water is going to start leaking out of your big water tower. And so let's say that there's just this little bitty hole. And so a drop of water falls. And then 5 minutes later, a second drop of water falls. And then 5 minutes later, a third drop of water falls. You would have a very low amount of current in this example because there's really not a whole lot flowing. Does that make sense? Now, if you wanted to increase the amount of current, put like a big gashing hole in the water tank, and if all of a sudden water starts flowing out at like a nice rate, then you'd have high current. So current is about how much is able to flow. Does that analogy make sense to start? That's current. Voltage then is all about energy. Voltage is about how much energy you can have. So imagine that this water had to fall this distance right here. Just to make it up, let's say that was 30 meters. Okay, that would be a certain amount of voltage. What happens if the water tower, though, were way higher, so it was way up here, and instead the water fell 100 meters? Now you'd have more voltage. Okay, and the reason why is imagine that I had to drop something from this high, or I had to drop something from that high. Which one's going to have more energy at the end of the day? Well, the one that falls further. Does that make sense? And so that's the analogy we use when we talk about batteries, is that batteries can be measured in both their current and their voltage. So I'll go back to this slide right here. Voltage is probably easier to understand. Voltage is how much energy change you have. Right? If I were to drop this little container from here to my hand, that's not a whole lot of energy, right? I'll use a different example. Let's say I dropped a penny from here to here. Is that going to hurt me? What if I went to the top of the Empire State Building and dropped a penny? That's actually illegal, if you guys didn't know. Because by the time the penny actually falls, the whatever it is, 200 stories that it has to fall, isn't that penny going to pick up a ton of energy? Right? To the point where it actually could cause some pretty major damage. That makes sense? So the height that it falls in the analogy is your energy. The same sort of thing kind of applies here, only remember how I gave the analogy of me taking the eraser and going from left hand to right hand? As we go around the circle, however much energy the electron has picked up and speeded up along the way, that would be your voltage. Okay? Now in terms of current is how many of them there are. Okay? And so since I used one electron going around, one eraser going around the loop, that would be low current. But what if I passed you 17 erasers to go around the loop? Then you'd have more current. So again, in this analogy, if I were to pass you a whole bunch of objects and send them around the loop, you'd have high current. If I were to send you just one object, you'd have low current. The speed or the rate at which it moves would be your voltage. So if I passed my first eraser to Cassie, she waited 5 minutes before it goes to Brady, and then she waits 5 minutes before there. That's low voltage. But if it's a hot potato and she goes boom, 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 that's voltage. So I did this analogy actually with my grade 9s one day. I think this actually made sense to them. These are now electrons. Okay. Here's 4 scenarios here. High voltage, low current. High voltage, high current. I don't want to drop them all. Low voltage, low current. Low voltage, high current. That makes sense? Okay. So if you can get those wrapped straight in your mind there, that's really important because we're going to use both of these terms, and you have to be able to do some minimal calculations involving these. Okay. These are some physics formulas that you guys that took it last year will recognize. This one right here is actually one that we need to use in our chemistry course at some point. It's the current is how much charge you have per second. That's the definition here. The amount of charge per second. Basically meaning if you have more charge, you have more current. If you have more charge, you would then have more current. Right? So that's when I dropped 5 pencil crayons, that's more current than if I dropped 1 pencil crayon. You guys feel like you get this? Okay, let me give you one last analogy, then I'll move on. I use this one also with the grade 9s. Imagine that you were trying to go from this classroom to just down the hallway to the office. Okay. If one of you walked down the hallway to the office, that would be a low amount of current. If the entire class walked down the hallway, then that would be a high amount of current. You guys are electrons, by the way, in this analogy. Right? So if you walk down to the office, that's low current. If all of us walk down to the office, that's high current. Now, if we're walking, that's low voltage. But if we're running, that's high voltage. Okay. There is actually one more variable that comes into play. We're not going to focus on it, but if you've ever heard of resistance before, there's actually 3 things that work together. There's your volts. There's your current. Current is measured in amps, by the way. This is current. The other thing that matters is ohms. I don't need you guys to do anything with this, but we may as well talk about it while we're here. Ohms is resistance. You guys ever heard of this term before, resistance? Maybe not there's resistance in a lot of different scenarios, but do you know what resistance means in terms of electricity? Resistance is what prevents the flow of charge. Okay. So the reason why I use this hallway analogy is imagine that the hallways are open right now. Is it easy for you guys to walk to the office? What if all the grade 6s or grade 9s were getting all of their stuff right here? Is it easy for you to make it through the hallway down there? Okay, that's resistance. In general, the way that you solve the resistance issue is you have thicker wires. Okay, you guys ever heard of gauged wires before, like an 8-gauge wire, a 12-gauge wire? The basic idea is that the thicker the wire, the easier it should be then for electrons to flow through. And the thinner the wire, the harder it is. Very, very basic example here. Jumping your car when the battery dies in the wintertime. Okay. I have two sets of jumper cables. I can't remember which gauges they are, but I have one that's like a nice thick, it's probably that wide, and I have one that's a little bit smaller, right? And I've tried this out before. If I try the smaller of the two jumper cables, there's not enough current able to make it through that thin wire for it to actually jump my car when the battery dies. But if I use like the thicker, the deeper wire, then it is. Does that make sense? So anyways, those are some basics of electricity. I don't need you to know resistance, but we are going to do some math in terms of both current and voltage. So current is measured in coulombs per second. That is this formula right here. The amount of charge you have per unit of time. I believe this is somewhere in your data booklet. In one of those pages that has units all over it. You have a data booklet there? Look through it. Thanks. Can you start at page 2? Yeah, there it is. Okay, if you turn to page 2 in your data booklet, if you have it nearby, there's a whole bunch of different units. One of them partway down the list is current. And it doesn't actually give you the formula, but it'll tell you kind of the units for current. What does it say here? Current is measured in amps, which is capital A, or current is measured in coulombs per second. What is a coulomb? A lot of electrons. Right? A coulomb is basically a large number of electrons. It's 6.25 times 10 to the, 18 electrons? So the more electrons you have moving per second, the more current you have. You guys have any questions on that first part? Okay, let's move on, because that's actually really not the point of my lesson today at all. But I need you guys to know the terminology. Okay, let's move forward. Okay, a little bit of history. I'm not going to spend a huge amount of time on this, but scientists, or sure, let's call them scientists, have known about electric charge for a long time. One of the first types of batteries was known as a Leyden jar. I used to have one of these, and I cannot find it. Otherwise, I'd demonstrate this for you. But I think you'll probably understand the generic concept here. What they did with a Leyden jar is they had like a doubly insulated thing here. So imagine that you've got a jar right here that is made out of glass. What's useful about glass in terms of charge? Anybody know? Yeah, it's an insulator. Yeah, exactly, right? So the outside of this thing is insulated right here. And on the inside, you put some foil. And apparently on this one, on the outside, you put some foil as well. Okay. And then what you have is a lid and a little ball sitting on the top. And this is similar to electroscopes. For those of you guys who have seen those before, where's my electroscopes? They're there. It's somewhat similar to this device. For you guys in grade 11, have you ever seen one of these before? Okay, you know what? I'm going to take the time to do this properly, because we'll do it next year anyways. Because I didn't teach you guys in grade 9, did I? Okay. You guys may want to come a little bit closer just so you can see the demos here. I'm going to show you guys some demonstrations of static electricity if you've never seen these before. So come close enough that you can see. Okay, this is called an electroscope. Basically, the concept is that this metal ball is on the outside, which gives me an access point, basically. But really what I want to focus on is on the inside. And very similar to this Leyden jar, it's got glass, trying to like provide a more or less an insulated system. And what ends up happening is I want to provide like a static charge. You guys know static electricity, like where you zap your friend, or like your hair kind of goes staticky. Okay. One of the ways you can do that is with just a basic fur here, and just like a plastic rubber rod like this. And so what I'm going to do is I'm going to charge this thing up, and this is going to be now very static. And one of the cool things about this is that if I touch that guy, next one. One of them works good, the other ones suck. Come on. There we go. That one worked good. Okay, grade 12's, you've already seen this before, so it's not new. Grade 11's, explain what happened. Any ideas? Magic. You want to take a stab at it? Why are those leaves all of a sudden separated? Can you see that from where you're at? That's not the way they were, eh? Here, I'll do that. Okay. I am providing some charge to this. There's some static electricity on here. Basically, this thing now has a whole bunch of electrons on it. Why is it separating? One of you guys? Yeah, because basically what happened is this thing became very negatively charged, static electricity. As soon as I touched it right here, it caused a conduction to take place where all of the electrons went through the little, I don't know, knob thing, I guess, right? Down through there and onto the two different leaves there. But these two leaves are so light and, well, light, I guess, right? They don't have a lot of mass to them. That when you have electrons and other electrons, what do like charges want to do to each other? Repel, right? And so then these two things, they move away from each other. Does that make sense? And so this is more or less how that Leyden jar works, is that slowly over time what you do is you just keep adding more and more charge to it. So you'd charge something up, however it is you charge something up, right? And then you'd add more charge to it. And then you'd charge it up, and you'd add more charge to it. And you'd charge it up, and you'd add more charge to it. And slowly over time, what ends up happening is the inside of this concept becomes more and more negative. I think we've reached the maximum capacity here, though, where like these two things, they're pushed apart as far apart as they possibly can. But if you can imagine that jar right there, I mean, basically there's like a chain on the inside that goes down and it touches the bottom foil. And all that's happening, I'll actually write this literally onto the board here, is that as you charge it up, you add electrons to this thing right here. The electrons go through here. And then now you start getting more and more electrons building up on the inside. Why don't those electrons leave? They can't. Because what's directly next to that foil? Glass. Do electrons have the ability to move very well through glass? No, it's an insulator. Right? There's actually a really cool thing you can do with this as well. What I just did there is I provided a negative charge, and then now that this thing is kind of like an isolated system there, if I just touch this is called grounding it. Where do the electrons go then? Back up into me and, yeah, into the ground probably. So I grounded it. So this is really cool. This is called an electrophorus. This actually makes a positive charge if you do it right. How do you get a positive charge? Yeah, lack of electrons. You steal electrons. So I'm going to charge this up right here. And so similar to how I rubbed the fur on this guy right here, this now, like this made this very negative. I'm now making this styrofoam very negative. But you know how styrofoam is also an insulator? What I basically have now is a whole bunch of electrons just sitting on the surface there. And then what I'm going to do is I'm going to put this guy on top here. Okay. Now what should happen is the electrons that are in the styrofoam are going to want to repel any electrons that are sitting inside this piece of metal here. Just grab breakfast, Joe. Keep going in a second. Well, you know what? I mean, 200 years ago, this would have been magic, actually, right? Has anybody ever seen the movie? Oh, it's with not Christian Bale. It's the other magic one. The Prestige? No. The Illusionist. The Illusionist. Anybody seen The Illusionist? There's a scene in it where he has his sword, and he makes his sword stand like straight up and down. And then it's like the whole like, oh, I can't lift the sword out of the ground concept, right? So he invites the prince to come up and let try to take his sword out of the ground, and it doesn't work, right? And then he goes up and he just lifts it up like normal, you know, making a mockery of the prince going like, well, why can't you lift your own sword up, right? But you know what he had actually built underneath the stage? An electromagnet, yeah, right? But since nobody else knew about how electric fields can cause magnetic fields, it seemed like magic to everybody else. But like nowadays, it's actually not that interesting. Okay, anyways, here's the concept. I'm going to charge this up with a whole bunch of negatives. Okay, and I'm going to put this on top. You can actually hear the crinkling sometimes. Because there's a whole bunch of negatives sitting on the surface of the, what do I want to call it here, the styrofoam, it's trying to push the negative electrons as far away as it possibly can. But the problem is there's really nowhere for it to go because all the electrons are going to be on the surface of this metal. Does that make sense? And so what I'm going to do is I'm going to touch it. Did you hear that? Okay, that was the electrons going from the surface of the metal into my body and probably into the ground. Now what I'm going to do is I'm going to lift this off of here, and I'm going to take my finger off. I know that seems kind of silly, but you know what I just did? Is I stole electrons from this piece of metal. And so this thing is now positively charged because I've removed the electrons from it. I'll do this again. You can hear the electrons jumping to me off of the metal. I'll do it one more time. So what I've now done is I've actually removed excess electrons from this thing. This thing's now positively charged. Not because it has more protons, but because like I literally stole electrons out of it. This negatively charged block right here repelled them upwards, and then my body basically stole them. So now when I bring this close and touch this there, see how that happened there? But now further electron stealing happened. Because this thing was positively charged, all the electrons that were in this piece of metal right here, they came up through the piece of metal, touched this thing right here. And now these are two positively charged leaves that are actually repelling each other. Does that make any sort of sense? This is a big part of what we do in Physics 30, by the way. Let me go back to this concept here. A Leyden jar then was a historic battery, where through similar sort of concepts, you have this little metal, I don't know, knob at the top here, right? And what you'd do is you would charge it up with static electricity. The electrons would go through the jar right here, and you'd have electrons all around the inside piece of foil, right? And then all you have to do is you'd have to just take the chain back out, and you'd have a lot of negative charge. Here's the downside to this, though. How long is that going to last for if you try to use it as a battery? Not very long. It's pretty much got a one-time use. Unlike a battery, which is a continuous electric circuit, a Leyden jar was like a one-time spark. So you could use it for something interesting, but like it was more like a static discharge, right? You guys have been shocked before, like with static electricity, right? Once you get shocked once, maybe you can do like a second shock or a third shock, but like after that, like it's kind of run its course, so to speak. Really, lightning is actually the same sort of concept. Lightning is a huge buildup of electrons on the bottom side of clouds that then discharge down to the Earth. It's actually a little more complicated than that, but that's enough for what we need. Once a single lightning bolt is discharged, it's done. Right? Now there could be other ones too, but that's static electricity. So, anyways, back to my concept here. Ben Franklin eventually coined it as a battery because he would then put multiple ones of these things together, and then that could give him like a little bit of electricity, basically. Kind of cool. Better erase the board here. This is another picture that I found somewhere. I think the basic concept is you grind this ball and you rotate it around in circles, and similar to how I took the fur pelt and I rubbed it against the top there, I believe that's supposed to somehow cause electrons to transfer. And then what happens is the grinding of this ball causes electrons to go through here, down here, and then this is the Leyden jar that's slowly but surely building up charge. Anyways. Now, it wasn't until the year 1800, and you probably have heard this name before because we actually named stuff after him. It's Alessandro Volta, and he actually discovered how to like build more of a continuous battery rather than this being like a one-time zap you sort of battery that's been slowly built up with static charge. He figured out how to make an actual continuous battery, and I ran out of time this morning for making one, so I will make one tomorrow. But have you guys ever seen me like take the clock off the wall and put it on like the shelf there with some beakers of chemicals? Were you guys in my class when I did that before? Okay, that's basically the concept. I'll do it again tomorrow if I get time. But this is basically the idea of a battery, is that electrons would then go through here, and then through here, and then through here, and then through here, and it would make a continuous circuit. And if the electrons can keep going in a circuit, that's a little bit better than static electricity, because static electricity is a one-time zap. Current is a continuous loop. Make sense? Okay, so let's talk a bit about some of the terminology. Once Volta basically discovered, hey, I can make a continuous circuit going on here, and we can do something with electricity, we need to apply some more names to things. You guys are probably already familiar with some of these concepts. All batteries, or as we call them in chemistry, all cells, have two different sides to the battery. There is the positive side to the battery and the negative side to the battery. This actually makes sense. Because, similarly to what we've been talking about, don't we need to have somebody who gains electrons? And simultaneously, don't we need to have somebody who loses electrons? So there have to be two sides to the battery. One's positives, one's negative. And the way we name them is that the positive terminal is called the cathode, and the negative terminal is called the anode. And that really just goes with the way we name cations and anions, right? Cations are positive, anions are negative. Cats have pause. So that's how you know which one is which. And I mean, if anybody ever had to jump their car in the wintertime, like actually attach the leads there, right? Like red is the positive one, and black is the negative one. That's just the colors that have been designated for things. So red is the positive, black is negative. And basically the idea is that electrons, you guys can probably highlight this, electrons always go from the anode through the circuit to the cathode. They always go anode to cathode. I want to explain that for a little while here. Do electrons like being by other electrons? Because kind of like we even saw in that little demonstration right there, electrons and other electrons are considered to be like charges. Like charges repel. Negatives want to spread out from other electrons. So imagine that you have, on this terminal of the battery, you have a whole bunch of excess negative charge. Do all those negatives want to stay there by each other? No. So what ends up happening is, slowly but surely, the electrons try going over to the positive side of the battery, because don't negatives want to become attracted to positives? Right? Isn't that kind of logical? Now, ideally, the negatives would just go through there. But we build some sort of barrier, some sort of way of separating them, prevents it from going the short way, and it has to go the long way. This is like my left-hand, right-hand analogy. I could take a racer and go from left-hand right to right-hand, but instead I'm going to put a big barrier here. So the only way to go from here to here is through the big loop. You know what I'm saying there? So, and then I think this makes intuitive sense. Negatives, electrons, want to go away from other negatives and go towards positives. If that doesn't work, I also memorized that it goes from A to C. That's alphabetical. So if that helps at all. Electron flow is always from anode to cathode. Sound good? Okay, you can have a couple of different types of batteries. You can have batteries where there's just one battery, like say this one right here. You ever tear apart a basic battery that goes in your calculator? It looks something like this. You've actually got like a rod that goes down the middle, and that's actually one of your electrodes. I think this one's the positive. And then the actual outer container, the container itself is actually the negative one. Do you guys know that? That's the way that those batteries work is that this one's the positive and that one's the negative. And then see how there's this paste in between it here? When the electrons want to go from one to the other, it physically can't because there's this barrier in the way. So what ends up happening is this little protruding thing right here goes to, usually it's like that little springy thing that's kind of in like a device, right? And then it runs through a circuit, and then eventually the circuit ends where there's that little protruding knobby kind of thing that goes on the other side and goes to there. And so that's your basic battery. Now, a 1.5 volt battery is just one of them. But if you were to combine a whole bunch of them together, we actually call it a voltaic pile. I had a picture that way back here. This was Volta's idea, is rather than having one battery, he eventually hooked up a whole bunch of batteries all in a row and made a really strong battery. Right. So like this thing right here is one cell. It could be like, say, 1.5 volts. This one could be another cell. That's another 1.5 volts. Here's another one, that's 1.5 volts. Well, add them all together, and now you don't just have a 1.5 volt battery, you might have a 12 volt battery. Does that make sense? You guys know the term like connecting things in series? Ever heard that phrase before? Like a series circuit? Basically, you're combining them together. So that's kind of what this picture right here is going for. Is this would have been 1.5 volts, that's 1.5, that's 1.5. Put a whole bunch of them together, and all of a sudden now you have a 9 volt battery. So, okay, other terms I need you guys to know. The term primary cells. You can probably guess the definitions of these. A primary cell is a battery that runs, and then once all of the electrons are run through their loop, it's now dead. So again, using this little battery example right here, if the electrons are running through this section right here all the way around to here, there were a whole bunch of electrons here. I'll even try to pick them up with my device here. So there's a whole bunch of electrons. The electrons want to go from here to there. Makes sense? But they can't. We're preventing them. So we send them around the loop. Okay, now they made it there. Because I used a lot of electrons, that would be a lot of current. If I used fewer electrons, you'd have fewer current, smaller current, right? Anyways, once all the electrons have gone here, if every single electron is now moved, the battery is basically dead. That's a primary cell. A secondary cell, which I think is on a future page here, a secondary cell can be recharged because all you do is you take some electricity and you force the electrons to go back to start. And then they can go through the loop. And then your cell phone dies, you plug it back into the wall, and you recharge it. That makes sense? So primary cells use once, secondary cells be recharged. Here's actually a really common reaction if you want to look at one. This is your car battery, actually. Your car battery takes lead solid plus lead 4 oxide plus sulfuric acid. And when you are using your car battery, it goes this way. But your car has a device called an alternator, which basically allows you to reverse the charge as you're moving. And you can actually make the electrons, rather than going this way here, you can actually cause the electrons to go back the other way and recharge your car's battery, which is really brilliant because otherwise, slowly over time, your car battery would die and you have to replace it. So really, your cell phone works on the exact same principles. Does that make sense? Sweet, moving on. Okay, so let's talk a little bit more now about the composition of these batteries. I've already introduced two terms. You have to know the term electrode. Okay. The term electrode really refers to one of two things. Either it's an anode or it's a cathode. Okay. Anodes are negative. Cathodes are positive. And the electrons go from the negative to the positive. Because electrons want to go away from other negatives, and they want to go towards positives. Who's losing electrons then? The negative, right? The negative is undergoing the loss of electrons. The positive is actually undergoing the gain of electrons. And for some people that seems weird, because some people would think, hang on, that one's gaining electrons. Shouldn't the thing that's gaining electrons be the negative? But the reason why it's gaining electrons is because it's positive, and positives attract electrons. Can I say that one more time? Because that's really important. Some people get confused and they think, hey, it's gaining electrons. They would think, hey, shouldn't things that gain electrons be negative? Because electrons are negative. If you're taking more negatives, shouldn't you be the negative? But that's like the reverse. You're not considering the cause. The reason why the electrons are moving in the first place is that electrons do not want to be by other negative charges. Electrons want to be attracted to positive charges. Therefore, positive things gain electrons, negative things lose. Does that work? So you now need to be able to memorize then that your oxidizing agents are your cathodes and your reducing agents are your anodes. Okay, and that's kind of what I have sitting on the slide here. I actually learned a silly mnemonic when I was in high school that stuck with me. Remember how I taught you how Leo says gur as a way of doing this? My teacher taught me that it was Leo says gurk. So silly. But like, seriously, like, it's been 15 years later, I still remember this stupid thing. Leo says gurk. No, it doesn't. But it works, I still know it. So, loss of electrons, oxidation happens at anodes. Gain of electrons happens at cathodes. Okay, I'm going to skip ahead here. I want to talk about a simple way of drawing a basic battery. So if you guys can find this slide here, one of the skills I need you guys to have, it's really like a two-directional skill. I either need you to be able to look at a drawing of a battery and tell me what is going on, or I need you to be able to draw a diagram of a battery. I either need you to be able to look at the diagram of a battery and know what is happening. Okay, the electrons are going here. This is the positive. This is the negative. Okay. Or if I don't give you a label diagram, I need you to be able to draw your own diagram instead. Okay. Now, on the diploma, by the way, they don't make you do written response. So really, we're mostly focusing on the other one, where I'm going to give you a labeled diagram and say, explain to me what's happening. Okay. But I want to practice both. So this is your basic concept of how like a battery would kind of look. This is your stereotypical drawing. you've got two different pieces of metal sitting right here. These represent your positive and your negative electrodes. Okay? It doesn't really matter which one is which, whether this is positive or this is negative, because honestly, like say you pick this one positive and that one negative, well, all you got to do is flip the two beakers around, and now they're on opposite sides, right? So I don't care which one is which. But let's say we start labeling this one here. So go with me here. Label this is your positive. Label this is your negative. We can now do some more further labeling. For example, this could then be your cathode. This would be your anode. Okay, now where do electrons normally want to flow from? From anode to cathode. Now ideally, the electrons want to go from this piece of metal right here. There's a bunch of electrons on this piece of metal right here, and they want to get to that piece of metal right there. It would be great if I could just literally touch them together. They would just transfer. But can you guys see how by the physical structure of this, there's like a barrier in the way, right? Like the mere fact that these things are in beakers with this big U-shaped thing in between there, that is going to prevent the electrons from going directly from here to here. So what's going to happen instead is the electrons are going to go through the wire, and they're going to go that way there. Okay? And then if this right here is a device that then needs electricity to run, now you have electrical current. Fair enough? So electron flow is going to be going this way. Electrons go that way there. It means I can label a few more things. I can also say that this is undergoing the loss of electrons, and this is undergoing the gain of electrons, which means that this must involve a reducing agent, and this must involve an oxidizing agent. Well, how many oxidizing and reducing agents are there out there? There's tons, right? We have a whole table full of them. Some really common ones are like lithium. Anyone have any idea why lithium is really commonly used in batteries? Consider its placement on the table. Find your data table for a second. Find where lithium is. It's like way at the bottom, which means lithium is fantastic at giving away electrons. No, accepting electrons. Yeah. No, hang on, lithium solid. Giving away electrons. For example, this thing right here could be lithium solid. Because lithium solid is like literally like the lowest right-hand side metal we have. Does lithium solid want its electrons? No. And so since lithium solid does not want its electrons, those electrons can now start going through the wire right here. All we need then is somebody who's willing to accept those electrons. Do you guys know what's a really common pairing to throw with lithium in batteries? It's actually not on your table. Lithium and cadmium. Ever heard of that before? Lithium-cadmium batteries? Sometimes they use nickel, but I'll use nickel right here, I guess, as an example. What ends up happening then is it's actually not nickel solid you want. It's nickel 2+ ions you want to have sitting in the solution. Because what ends up happening is this lithium solid turns into lithium ions, and it spits out some electrons. And those electrons then can now go through your wire. Those electrons then go all the way through the wire over here, and now there's electrons sitting here. Well, you know who'd love to have those electrons is somebody like nickel. Because what's going to happen when nickel 2+ adds to it some electrons? It'll turn into some nickel solid. You'll actually see some buildup on this electrode right here as some nickel solid gets made. And what you'll actually see on this electrode right here is that as the lithium solid decomposes in a way, you're actually going to see it like waste away and corrode, and like it'll eventually like have pieces like fall off of it. You guys have seen me put magnesium in hydrochloric acid before, right? That's essentially what's happening here is the magnesium is like dissolving and turning into magnesium ions. That's what's happening here. Lithium solid is dissolving, turning into lithium ions. Through that process, it loses some electrons. Well, where do the electrons go? Well, they go through a nice conducting wire all the way over to here. Now there's a bunch of electrons just sitting over here, which is great because here's someone like, say, nickel 2+. Nickel 2 plus would love to have some electrons, so it takes electrons, makes some solid nickel, and you get a bit of like a corrosion there. You guys ever seen what happens to like your AA batteries when they start to die? You ever see that like white sort of like buildup, right? That's kind of what's going on right here, is that something new is getting made in a way, right? And actually that's the reason why the battery works the way it does, is that the battery eventually dies, these ones right here, because as the electrons leave the outer coating right here, this outer coating right here eventually starts to dissolve. And eventually what ends up happening is like the paste on the inside, it starts to leak out because this outer coating right here, as it loses its electrons around to here, eventually like dissolves, so to speak. And eventually there's enough of a hole in it, and then the paste starts to ooze out, and you see all of that like white pasty stuff coming through. Does that make sense? Let me go back to my battery here. So, all batteries then can be drawn in more or less the same sort of way, but the thing that changes then is, does it always have to be lithium and nickel? Well, no, it can be really any two oxidizing and reducing agents. Now what comes into play is the further apart they are on that table, the more voltage you get. Hear that one more time, that's really important. The further they are apart on the table, the more voltage you get. And that's why we use lithium, because lithium is so low. If I can find something that's really low and really high, I've now made a very, very high voltage battery. Let's talk about why. You guys with me back there? Okay. What is voltage again? Voltage is not how many electrons transfer, it's how fast they transfer. I want to come back to the Boolean concept here. Remember how we talked about how, like, a grade 12 kid and a grade 3 kid get into a fight for lunch money? Who wins? Well, the grade 12 kid wins, right? Well, what happens if you have two, like, in the middle sort of scenarios? We have, like, a grade 8 kid and a grade 7 kid. Okay, the grade 8 kid is going to win, but do they win by a lot? Is it going to be more of a long, drawn out process where it takes a little while for someone to actually, like, win the stealing for electrons? You know where I'm going with this? So the further apart your oxidizing and reducing agents happen to be, the faster it's going to occur, because you have a really big bully fighting a really big wimp. It's just going to happen immediately, right? Whereas if you have something here and here on the table, it might still be spontaneous, but like it's not quite as efficient in a way, and therefore there's not as much energy because they can't move as fast. Current is about how many move. Voltage is about how fast they move. So that's why we build a lot of batteries out of lithium. Car batteries, by the way, are built out of lead. Can you guys find the top left-hand corner of your table? The lead reaction is like the third one or the second one from the top. You guys see that one up there? It's like, actually, I have a table on this in these notes here. Here it is. Can you guys see this one right here? PbO2 plus SO4 plus 4H plus gives that one right there. That is actually the chemical reaction that takes place in a 12-volt car battery. And so the reason why this one occurs is that this one is really high up. And the reaction is this stuff right here reacting with, this is one of your terminals. The other terminal is lead solid. And because of that, that has a relatively large difference between the two. And that causes it to be quite a high voltage. Okay. And that's why in a few minutes I'm going to spend more time talking about these numbers over here. But these numbers then can help you figure out how much voltage you have. Is that going to make sense? Let me go back to my picture here. There's a few more things I need to label though. This U-shaped tube here. People often wonder, what's the point of this tube here? Because aren't the electrons going all the way through the circuit? So why does there have to be this connection right here? And it has to do with the concept called polarization. Okay. I want to talk about what's going to eventually happen. All of these electrons right here, they want to leave. They want to get out of this piece of metal here. Because really, lithium solid doesn't really want electrons. But you know what eventually happens over time is the lithium solid turns into lithium positive. And eventually this beaker starts to become quite positively charged. Why is this beaker positively charged? Well, because it's spitting out a whole bunch of lithium positives there. Well, hang on a sec. Weren't these electrons being repelled by other electrons and being attracted over here by positives? But what happens if this beaker right here starts to have a whole bunch of positives in it? Why would the electrons want to leave anymore? Okay. Furthermore, take this beaker over here. I know it's nickel 2 plus, but what's happening is your nickel 2 plus is attaching itself to the surface of this metal right here, and you're losing all your positive ions because all your positive ions are turning into solids. What happens when you lose positives? You're actually going to basically have more negatives left over. And so what ends up happening is this beaker here slowly but surely becomes negatively charged. So consider the electron's perspective. At first, the electrons have no problems going through the wire. Hey, there's a whole bunch of electrons here. Let's move. Let's get out of here. Sometimes I use a party analogy. Boys and girls at a different party. There's a party going on in this beaker right here, and there's a whole bunch of electrons. So those are the girls. And there's so many girls at this party over here that they go, let's go find where the boys are hanging out. Right? And so eventually they decide to go all the way over here and find the party over here where, hey, there's some positives over at this party here, right? But eventually what ends up happening is as the negatives leave right here, these negatives leaving cause positives to show up in this beaker. Well, now what reason do you have to leave anymore? You know what I'm saying there? Right? I know that there were positives way over here that these electrons were trying to attract, but as soon as this solid loses its electron, it also makes a corresponding positive. So, long story short, beakers and batteries over time become polarized, and eventually the battery stops running. So what you have to have is this thing right here called a salt bridge. And what happens in the salt bridge is we put an ionic compound in. Usually the one we use is potassium nitrate, although it can be many things. And what ends up happening is this salt bridge through the principles of diffusion. Does everybody know what diffusion is? From biology? Like where things go from high concentration to low concentration? What ends up happening is the salt bridge causes nitrates to diffuse this way to counterbalance all the positives that are showing up over here. And it causes potassium to diffuse this way to counterbalance all the negatives over here. And it prevents the cell from becoming too polarized. Otherwise, what happens is you have a beaker here that becomes positive and a beaker here that becomes negative, and then the electrons have no reason to keep flowing, because why would electrons want to go away from a positive? And why would electrons want to go towards a negative? I'm going to show you guys this a few more times. Like, we're not going to do this just once, but that's kind of the basics of a battery. Anybody have any initial questions? Okay, what I need for you guys to be able to do is, like I said earlier, you either need to be able to interpret a battery diagram, or I need you to be able to draw one for me. So I've got a whole bunch of slides here, we'll do some of those. So why don't we go do, let me skip ahead here. Here, can you guys find this slide somewhere way further in your notes? And why don't we try an interpretation one first? I'll give you a picture. We'll try to figure out what's going on. Can you guys find this one? Okay. So what we've got going on here is silver and copper. Okay. Silver and copper. And I've labeled this one here with this one being the anode and this one being the cathode. The reason why I know how this is working is that anodes always involve the loss of electrons. LEOA. Cathodes involve the gain of electrons. GERC. Or another way of looking at it is that the reason why this is negative is that there are so many negatives being built up on the surface of this metal that these negatives want to go through the wire and get away. Why are there so many negatives on the surface of this metal? Well, it's due to this equation right here. Copper solid is dissolving in a way into copper 2 plus and 2 electrons. See how this copper right here, it's kind of pointing out to like a point right here? Because what's happening is all of the copper is falling off of this metal rod right here and forming ions, which is why this is blue, by the way. Copper is blue in solution. And there's a whole bunch of electrons. But kind of like with my, I guess, boy-girl party analogy, there's so many electrons over here that the electrons are like, let's go find the opposite sex. Right? So too many boys, I guess, at this party here. So some of them decide to go, hey, let's go searching for somebody over here. Does that make sense? Well, the reason why all these electrons can find somebody is that over here you've got some silver ions sitting in this solution. And these negative electrons are very much attracted to those positives. Hopefully you can see in the diagram, these positives then, see how there's a bit of a buildup down here? Because what's happened over here is the silver ions took the electrons and made silver solid. But here's the problem with the solution then. As these coppers are getting kicked out, this beaker is becoming very positive. Because as the electrons are being lost, when you lose electrons, this beaker now becomes positive. That makes sense? And as all of these positive ions right here start to build up right here, if you lose the positive ions you have here, this beaker starts to become very negative. And that causes an issue. Because why would these electrons want to leave a positive situation? No pun intended. And why would these negatives want to join a negative situation? Oh, that's good. I didn't intend for that. Right. So this is where the salt bridge comes in. With this sodium and nitrate right here, through the process of diffusion, positive sodium ions are going to diffuse into here to then neutralize, in a way, the negativeness of that beaker. And negative ions right here are going to diffuse into this beaker to diffuse that situation. And that way the cell can keep going. The salt bridge is actually critically important, because otherwise your battery runs for a little while, it becomes polarized and then stops. Does that make sense? You just have to build a salt bridge where you build a solution that's inside there. Usually what you end up having happen is there's a cotton plug sitting right here in this U-shaped tube. But what can end up happening is ions can diffuse through it like a membrane. You know, you guys know membranes from biology, right? So diffusion can take place through this, losing my board here. Through this little plug right here. I'll show you how we do it in our lab as well. So we could label a few other things then. If this is the loss of electrons, then you need a reducing agent here. And if this is the gain of electrons, you need an oxidizing agent. And I could actually label those. Who is the reducing agent? The reducing agent is solid copper. Who's your oxidizing agent? Who is our oxidizing agent? It's actually the silver ions. This is really important here. It's not the silver solid. The silver solid is the product that gets made, but what you really need is the ions in this solution. And so you actually have to put a whole bunch of silver pluses there to begin with, so that the positive silver can attract the electrons and coat the outside surface like this. As soon as you run out of silver ions, the battery dies. Does that make sense? Okay, I'm clearly going to have to do 2 days on this, but that's okay. Whatever, it is what it is. Okay, let's go back here. Let's talk about voltage for a bit now. I've skipped this. Can you guys find this slide here maybe now? So I haven't covered this until now because I didn't think now it was appropriate yet, but now we can talk about voltage. Here's basically the way this table works. It's a ranking system. In the middle of the table, right in the middle, hydrogen has been chosen to arbitrarily be called 0. There's actually not a whole lot of rationale as to why, other than I think 1, hydrogen is the first element in the periodic table, sure, and 2, it's more or less dead center in the middle of the table. So can you guys find the H plus going to H2 gas reaction right in the middle of the table? That one has been chosen to have a value of 0. It's considered to be like the neutral state. Okay. Anything above it is considered, was it positive? Everything below it is considered negative. Here's the way this works then. If you want to figure out the voltage of your battery, your cell, you just need to know the difference between your oxidizing agents and your reducing agents. This is actually really simple. Find the 2 half reactions, find the 2 voltage values, and subtract them. That will give you the voltage of your battery. You got to find the difference between the 2. It may mean you're subtracting a negative number, but you're trying to figure out the raw distance between this number up here and this number down here and figure out how far apart they are. So let me do an example here. If I could, can I go back to the one we were doing here with copper and silver? I believe I know copper's value. I believe copper is 0.34 volts. You guys find that one on your table there, copper? Just make sure it's 0.34. So in your data booklet. I don't know silver's off the top of my head, though. So find silver's voltage number there. 0.80. Can you guys all find those numbers that I'm referring to? Okay. These numbers are very similar to a burette in that you never consider them with just one number. Okay? These are numbers that are relative to each other. Okay? So like copper does not have 0.34 volts and silver does not have 0.80 volts, but collectively the voltage of this battery is going to be 0.46 volts. Can you guys figure out how I pulled that number out of thin air? Subtract the two. Yeah, the difference between them. Okay, very similar to your burette. When you take your initial reading, it's meaningless. When you take your final reading, it's meaningless. But put them together, and you actually have something. So that's how this table works. It's somewhat arbitrary as to where they started. They could have had the very, very, very bottom number, lithium, be 0, and have everything go above 0. That was a possibility. But they just decided to make the middle of the table be 0, have some numbers go above, some go below. All you've got to do is subtract the two numbers, and that's the voltage of your battery. Does that make sense? Okay, let's try another example here. Let's do, let's try one where we're going to label something here. Let's do this one here. We'll have to come back to some of this tomorrow. Here's a very basic concept battery. Now, I've skipped on some slides a notational issue. If you ever see this notation right here, it's actually telling you what your battery is made out of. The way it works is that the first little section right here is your anode. The last section is your cathode. It always goes alphabetical. This is your anode, this is your cathode. And then this section right here is the electrolyte, which is like the liquid solution that your anode gets placed in. And this is your cathode's electrolyte. So in a way, I can actually label this beaker. This is going to be scandium solid right here. In the beaker, I'm going to put some scandium 3+ ions. Then the double line is the notation for your salt bridge to indicate that you have to have a barrier, because you really want the electrons to go the long way around. You don't want them to somehow phase through. So this is your barrier, which is your salt bridge. And then in the next beaker, you want copper 2+. And then your piece of metal here is copper solid. Does that make sense how the notation works? Anode, anode's electrolytic solution. Cathode, cathode's electrolytic solution. We should now be able to label a whole bunch of things. So I'm actually going to use a new color now. If the very, very first thing here was the anode, I can tell you that this is now the negative pole of your battery. And if copper is your cathode, I can now tell you that it's the positive pole of your battery. Furthermore, anodes are the thing that lose electrons. And cathodes are the things that gain electrons. You guys able to follow so far? Which way are the electrons going to go? Are the electrons going to go from the scandium to the copper or from the copper to the scandium? Good, you're right. Yeah. They go from the anode to the cathode, so electrons are going in this direction like that. Now, if we were to zoom in a little bit closer, hop on the Magic School Bus and zoom into this beaker right here, what are we seeing occur? Yeah, breakdown. That's a good way of putting it. This scandium right here, if I were to write a reaction, scandium, yeah, let's do it again. Scandium solid is breaking down into scandium 3+. And it's got to be 3 electrons, right? That's the only way this makes sense. And so those electrons are now able to leave. What's happening to this electrode right here? It's breaking down, and it's like wasting away to nothing. It's eventually going to like dissolve. As soon as this thing has dissolved, the battery dies. That makes sense? That's one way in which the battery dies. What's happening to this beaker, though? It's now becoming very positive. which means that through the salt bridge, I'm going to need to have some sort of negatives coming through the salt bridge to prevent polarization of the cell. I don't care what the positives or negatives are. Sodium nitrate, potassium nitrate, sodium chloride, I don't really care. Some sort of ionic salt works. By the way, another little nifty trick here is that anions flow towards anodes. In your salt bridge, anions, those are your negatives, right? They always flow towards anodes. That helps. Now let's talk about what's happening over here. Which is more important in this beaker? Is it the copper 2 plus or the copper solid? I agree. You want to take a stab at to why? And it's taking those electrons that come through here and it's forming the copper solid. This copper solid is really a product. Does that make sense what I'm saying here? Because what's going to happen is these copper ions that are sitting in here, they are going to be absorbed by the electrons and they're going to form copper solid on the surface here. So really, I know I wrote copper right here, but it's not this copper that's important. It's these copper ions that are important. Because slowly over time, they'll become depleted as they build up solid copper right there. Right? Eventually, if I run out of these ions here, the battery could die. So there's two main ways your battery dies. Either your scandium runs out, or your copper ions run out. And then to finish this thought off, as all of these positive ions get attracted to this guy right here, it means this beaker here is actually becoming quite negative. So to counterbalance that, your salt bridge is going to diffuse through some cations, which makes sense because cations always migrate towards cathodes. So here's one of my equations. This was my oxidizing equation, scandium losing electrons. My reduction equation then would have been copper 2 plus picking up those electrons to become copper solid. If I want to find the voltage of this battery then, I find this guy's voltage number, I find this guy's voltage number, and I subtract them. But for some reason, I don't think scandium's in this book, is it? Okay, so we'd have to look that up somewhere else, but that's what we do. You do not actually. Good question here. You have to multiply the numbers to balance the equation, but you never multiply the numbers when you deal with voltages. That is a great question. I'm glad you brought it up. In order to balance the equation, you guys can see you'd have to times one equation by 2, 1 by 3. When you're doing voltages, that's irrelevant. That's not how that works. So that's okay to just leave that there. All right, let me see if I can find one more example and we'll call it a day here, because I'm going to have to do this more tomorrow. Here, this one's good. Okay, this is an old diploma question. I think I've given you guys enough now that you can answer this question. Let's do it as a group. I'm not sure it's in your notes, though, is it? Oh, it is too? Okay, good. I was on top of things. Okay, so here's a common thing they're going to do. They're going to give you a picture. It's going to be pre-labeled, and you have to just interpret what's going on. So I'm going to look at what's going on here. We've got some copper nitrate, we've got some cadmium nitrate. And we've got to figure out these following 4 things. 1, who's the anode? By the way, the anode has got to be either 3 or 4. Does that make sense? Who's the cathode? Well, whichever one I don't pick is the other one, right? Anion movement is either going to be this way or this way. This is kind of their way of quickly illustrating a salt bridge. It's kind of a cheating way of doing it. But they didn't actually draw 2 beakers. They just drew like a barrier here. So either anions are going to move this way or this way. And then finally, we want to know electron movement, which will either be 1 or 2. So here's how I go about doing this. I've got to figure out my beaker of stuff question. What I've got is copper 2 plus ions. I've got copper solids. I've got some cadmium 2 plus ions and some cadmium solids. That's roughly where they are in your data booklet. I don't know exactly the right location, but that's roughly where they are. Where's your spontaneous reaction? With those guys. Does that make sense? So who is going to be gaining electrons? Going this way, copper is gaining electrons. So I could write over here in this beaker here that the gain of electrons is taking place at the copper, and so electrons must be coming through here. The reason why copper is gaining electrons is because cadmium is giving them up and going the other way. So what's happening here is your cadmium here is dissolving away into cadmium ions, and the electrons are going through here. The copper 2 plus ions are then becoming attracted to this. There's some buildup around the outside. And now I kind of have the basic picture of my cell started. It was all based on my table. I had to know who was above who. Since copper is above cadmium, right? I'm going by memory here. Since copper is higher than cadmium, these copper ions will take the electrons, these cadmiums will give. I think I now have more or less enough to answer the question. Let's do the electron movement first. The electrons are going this way, so that's number 1. That makes sense? And then I wanted to know who the anode was. I haven't labeled these yet, but now I know that it's Liowa and Girk. Oh. It's dumb, but boy, it sticks in your head. So, okay, so if this is the anode, then cadmium, the 4 must be the anode, and the 3 must be the cathode. And then for the last one, we got to figure out the polarization of the cell. I'm going to draw this in a little bit more detail, and we'll call it quits for the day. What's happening right here is all your copper 2 pluses are being sucked towards this one right here. And so if all your copper 2 pluses are leaving, this beaker is becoming negative. And then right here, this is emitting, in a way, cadmium 2 pluses. Cadmium 2 pluses are being emitted. So this beaker is becoming positive. So what we're going to need then is negatives to migrate this way and positives to migrate this way through the barrier. Honestly, the easiest way of remembering this is that anions go towards anodes and cations go towards cathodes. See my negatives right here? They're going to need to migrate over here to counterbalance all these positives right here. And positives right here are going to have to migrate over here to replenish all the ones that are being lost. So anion movement happens to go towards the anode. So that's going to be number 5 then. I'm not done. I knew this was going to be a possibility. I took a long time on for other things, but you guys have any questions so far? Okay. Let's pick this up tomorrow, I guess. I guess my demo I'll have to wait for tomorrow now, too, if you want to watch electrolysis of water. So. Oh, can I do one last thought, actually? If I want to find the voltage of the battery, this won't take long. To find the voltage of this battery, copper is 0.34. Does someone have their table in front of them? Can someone find cadmium somewhere on there and find me its voltage number? Negative 0.40. Okay, so the voltage of this battery then is going to be 0.74 volts. Is that clear? And the reason why is that it's this number, subtract this number, but because it's in the negatives, a double subtract really means to add. Does that make clear? So since one is above the 0 marker and one's below the 0 marker, you see the distance between them? So this would be a 0.74 volt battery. You guys can now go back and redo those calculations for other questions. All you got to do is just find the two numbers and subtract them. You may be subtracting a negative, which means you're adding. Okay, sound good? All right, thanks, guys. We'll talk more about this later then.